Except we're not going to be at the board. I want you guys to try number 6. And number 6 will kind of complete kind of our big 4 series or Taylor polynomials that we need to know. So if you guys would use kind of the Taylor construction we've been working on, this is Maclaurin for e to the x. All right, so give it a shot. Isn't one of the real advantages to this one? Oh, thank you. Isn't one of the real advantages the fact that regardless of how many derivatives you do, the derivative of whatever it is still just e to the x? And so the hope here is that you caught on to that pattern pretty quick and you thought, well, f prime, f double prime, f triple prime, however far I need to go, it's all just going to be the same thing. And e to the centering point, which is 0, is just 1, right? And so for this, I'm hoping that you guys got this polynomial. Say p of x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And that would be your first 4 non-zero terms, right? This also asks for an nth term. So this is a little bit tougher than that other nth term we did. Anybody have a suggestion on what that nth term should be? X to the n. Over n factorial. Yeah, exactly. The n's match here. The n factorial and the n match.
How did you write that correctly? Because it asks for first 4 non-zero terms and the general term. Is that all you need to do, or do you need to write them separately?
No, in fact, you want to write them summed.
Okay.
Yeah, you want to write them summed up, kind of like in a simplified polynomial format. So yeah, definitely want to write those summed up. So this, I think, like I said earlier, this kind of finishes the big 4 series that you need to have memorized. Okay, because what we're going to do in the coming weeks, I guess it would be, is we're going to use these 4, and I'll remind you of these 4 today, and I'll keep reminding you a lot. We're going to use them to get to other series in a more efficient way. And so we'll just manipulate, adapt, do stuff to them, and get to these other series that would be otherwise really difficult, impossible, we don't want to do it because it would take forever situations. We can use these to kind of shortcut to those. So let me just remind you of what those are. We want the series for e to the x. So we'll put this off to the side here in a little box. So the series you need to know, or the Taylor polynomials you need to know, would be e to the x, cosine of x, sine of x, and then that one we looked at last time that's right below here, which is 1 over 1 minus x. Make sense? These are the 4 we're going to use these, and I'd say the 2 we're going to use the most would probably be this one and this one, e to the x and the geometric series. Use those the most probably. So I thought maybe a good way to finish this off before we move into our main topic of the day is for you guys, if necessary, look back through your notes. Maybe you have some of these already sort of kind of memorized. Why don't you write out the first 4 non-zero terms and the nth term for all 4 of those. Just wherever you got a little space there on your page. And we'll write these out a lot over the next several weeks. I don't know if we'll do it every single day, but we'll do it a lot. Bless you. Just as a way, hopefully, to help you get these memorized. So, yeah, let's get the nth term as well. I'm just going to write them up here quietly, and I'll unfreeze it.
No, this is your dog. This is your dog. Yeah,
I'm sorry,
like that.
I just have a question. If
Yes, sir.
you write your summation to the general term, and then you put equal signs and then the function, that's allowed, right?
Is n going from 1 to infinity or 0 to infinity?
Well, how you wrote p to the x up there.
P of x, right?
P to the x, you wrote e to the x.
Well, so then we can get into some issues there. So the only way that we can say that that's really equal to e to the x is if n starts wherever it needs to start, like in this case 0, and goes towards infinity.
Okay.
That's the only way we can say e to the x actually equals.
Okay. So like when you want to write like the first four terms and the general term for each of those, you
Sure.
want to avoid putting equal sign.
Yep, but you certainly could put this.
It is.
Like approximately.
Yeah, e to the x is approximately equal to.
Yeah.
Sure. That works.
Do you want the first four non-zero terms or just the first four?
First four non-zero
Okay.
and the nth term.
Including for cosine and sine.
Yep.
Have we done that?
Yep, so cosine was in the video, the intro video,
If you watched it,
and I think we did sine once or twice.
the sign's on like the last page, like literally right here.
I don't remember finding the nth term. That's what I meant.
Oh, zero factorial one. It is a little janky.
0 factorial is 1.
I don't know how to write that.
We can talk about why that is again if you want, no problem. We'll bring it up. Let's bring it up once we've settled on what we have up there, and then I'll just remind me, we'll do it.
N plus one?
Who's that?
Someone never watched live.
We got the second term, third term, it's zero, so it doesn't
I never noticed you did that. And I was like,
Okay,
oh,
true.
American.
I'm not lying.
What?
I already don't believe it.
Like, wow, cool. It says, in players is sprinting down.
It was Mr. Because we heard it. That was Mr. Blake.
What do you do? Same thing for boys, we like stand by the under the basket. On the home side, we like split up and stand, and then just cheer. It's fun when the other cheer teams come, because then they face on the wall, and you're like cheering. For the boys game on Wednesday, they came
They scare you.
and they lost.
Was he still sprinting while he said, "Did I scare you with this?"
But when he's got like 5 feet in front of me, he stopped. And he goes, did I scare you, Liz? And I'm like, I had the feeling
Was
that
he
it was
sprinting
you.
just to scare you?
Yes.
So I think I got all those up there. Feel free to check back and see if we agree. I drew a graph up here for, hey guys, check this out please. Drew a graph up here for e to the x, and I thought we've done something like this before. I thought I would write the Taylor polynomial for another equation here. So the first term, as you guys know, is 1. So y equals 1. Would you guys agree that, as Josh kind of tongue-in-cheek said, that's pretty close? That's pretty terrible approximation, other than at the centering point, right? Do you see how at the centering point, which is 0, it's perfect, right? But once you move off the centering point, once you're over to the left or the right, it gets much worse. So then we add the second term in, and now you can see it's a little bit better. Make sense? And then you add in maybe a third term. Oops. Over 2. How about that? You can see that it got a little bit better, right? But once you move a little ways off 0, once you get outside of like -1 to 1, it gets terrible again. And then we go x to the third over 3 factorial, which is 6. Now it's getting better and better, isn't it? And you can see that interval of convergence is going from here to here to here to here. It seems to be getting larger and larger. But you got to admit, like what we've done for the last couple of days, I think you guys have done very, very well. But you got to admit, when we say write the first 4 non-zero terms or the third degree Taylor polynomial, would you guys agree with me that it's off? There's error, isn't it? Because how many terms would I need if I was going to keep going with this and say, well, let's put in another term plus, how many of these and one more terms would I need? Oops, I would need infinity more. Yeah, that's right. So x to the 4th over 4 factorial, so that's 24. It's getting better and better. You can see that the more terms I have, the better this gets. But it's never really going to be enough to be perfect, right? at some point I would have to stop and say, well, I've written out 10 billion terms or whatever, and even if I did somehow write out 10 billion terms, that still wouldn't be enough, would it? Remember this. Please remember this. A Taylor polynomial will only perfectly match the original graph at the centering point. The moment you move off the centering point, there's error. And the more you move off the centering point, the more error there is. Make sense? Can you see it represented up there? Yeah.
So it doesn't really make sense. But say you have like a lot of terms.
Yeah.
A lot of terms, like
10 billion.
10 trillion.
10 trillion.
And then you move away from your starting point of 0.0001. You're still off.
Still going to be a small amount of error. But the point is, the more terms you have, the error gets smaller and smaller. And you're going to be shocked at how small of a number of terms is needed to make the error pretty tiny.
Yeah.
As long as you're somewhere near the centering point. So what we're going to explore today, I'll get your question in just a second, Liz. What we're going to explore today is kind of what you're getting at. It's how bad is it? What could be the worst error that could happen from what we just did? And when you stop and think about that, isn't that the kind of thing that maybe an engineer would ask? You know you're never going to be perfect, but is our error acceptable? Is it tolerable to be within 1/1 of something? Or is that not even close? Should it be a billion zeros and then a 1? Would that be acceptable? You know what? You can control that. You can control that. Liz, question?
So is this that thing where like the more terms you have, it gets accurate like more off of the centering point, or does it get
It gets more.
accurate, like
No.
all the way?
What do you mean all the way?
So like as you add, so you have your centering point,
Yep.
and then as you add terms, does the accuracy go out like this as you add terms?
So we want to be careful about our terminology here. Sure. So you get your centering point, and as you add more and more terms, then the interval of convergence, which we've talked about,
Yeah.
which would be describing what if we had an infinite number of terms. So the number of terms was approaching infinity. That could potentially expand out pretty far, or it could be just limited.
Yeah.
But realistically, we can't have an infinite number of terms. Wouldn't you love that? That was my assignment for you. Hey, this weekend, write out an infinite number of terms for e to the x's power series, right? We'd all know that that was just totally silly. So the point is, you know you're going to have to stop at a finite number of terms practically. And so wherever you did stop, what we're going to investigate today is, how far off are you? Is it like this? Or is it like this? Or is it, can we not even see it? It's so tiny and so it's okay, right?
So if you were only worried about like 0 to like 0.1
Mhm.
or something, if you were only worried about that interval,
Yeah.
could you just do like 20 terms? And
Maybe.
you'd be fine?
You'd be able to calculate your maximum error based off that
Okay.
and say, hey, look, that error's okay. And then we're good. Okay, cool. All right, so then let's explore this a little bit. I think I mentioned last time this is some of the more terrifying looking notation. Yeah, I know there's a Z in there too. And so this goes back to Taylor's theorem, and I'm going to try to cut through the scary writing for you. I think there's some good stuff here. Let's break this down. Would you guys agree with me that error is expressed this way? Isn't error simply the actual value minus your approximation? Right? The true value, whatever it happens to be, if you subtract off your approximation, that gives you the real error. And so we're going to use this kind of notation for this, right? We're going to say f of x, which would be the real value, minus my polynomial. That's my error. Sometimes that's called the remainder, simply because, think why that's called that is with a Taylor polynomial. Like I said, you got to cut it off somewhere, and the stuff that, remained off the back, right? That's going to help us define and bound our error. So sometimes it's called the remainder. We'll call it error most of the time. So Taylor's theorem says essentially this, and this is, we're going to use some really specific symbols. This gets into whoever asked about the equal sign earlier. Johnny? Yes? No? Maybe it's Dylan?
Me?
Matt, maybe? Yeah. Sorry. It was one of you fine folks. Sorry I mixed you up. Notice this. It says f of x equals, not is approximately equal to, And then you all at this point probably recognize all this stuff, don't you? Isn't that just a Taylor polynomial? So f of x equals that Taylor polynomial all the way out there to the nth degree plus some remainder. Plus some remainder. And our goal is going to be to try to quantify and bound that. When I say bound, I mean give it a boundary and say, hey, we know there's an error, but the worst it could possibly be is this or that. Okay? How is it that we find this error? It's right here. And we'll look at this. We'll look at this in a slightly different form. We're gonna look at this in what's called the Lagrange form of the error bound, or the Lagrange error bound. Yeah. Lagrange. Okay. So can I give you guys a word of caution? This can be one of those things where if you like mentally check out for 10, 20 seconds, you're going to be like, what? Oh, I thought this was this other thing. So you're going to be tempted, after I'm done explaining this, you are going to be tempted possibly to think this. Oh, Lagrange error bound? That's basically just like the alternating series error bound. The truth is, sometimes it is, and sometimes it's not. Okay, so Lagrange error bound, let me put it like this. Lagrange error bound is like the bigger overarching way of describing error. And the alternating series error bound is a very narrow way to describe it because the alternating series error bound only applies to alternating series. So that's why I say sometimes they're going to seem like they're the same thing, and other times they're going to seem like they're not the same thing because technically they aren't really the same thing. Lagrange, think of it as like the broad perspective, right? It's like saying this school is full of students and saying there's a boy. Does that mean all the students are boys? No. That's just a specific example of a student, right? Everyone is a student. We could say, think about it like this. Think of describing our whole student body as saying, hey, they're all students. There's one of them right there, and he's named Dylan. Does that mean that every single student is named Dylan? Yes. As far as I know, Dylan? No? Liz.
Oh, it's Dylan.
Anyways, so let me kind of guide you through the nitty-gritties here, the details, see how this works for you. I'll get your question in a second. I got some good momentum here. Let me get you through the details. So do you guys recognize this? Isn't that just an expression for error? Actual value minus my approximation. This could also be described as the remainder, although, like I said, we'll far more frequently use that. But just so you know, sometimes people call it R sub n, remainder based on n, the nth polynomial. And here's how we do it. It's the absolute value of x minus c to the n plus 1 over n plus 1 factorial times the maximum value of whatever that thing is. So let me put it to you like this. I think there are 3 parts to this, and of the 3 parts, 2 of them are incredibly formulaic. Like, in other words, you go plug, plug, chug, right? The third part is not so formulaic. The third part, you're going to have to think a little bit, okay? So I think parts 1, can you say that's a 1? Parts 1 and 2, those are supposed to be a 1 and a 2 there. Parts 1 and 2 are very formulaic. Part 3 over here, that's the part you're going to have to think about a little bit. Let's talk about how this formulaic stuff works first. I'm going to approach this from, let's do all the easy stuff first, and then we'll do the hard thinking at the end. Okay. So over here is kind of your guide. The series, as you might expect, is centered at C. So as long as you know the centering point, then you know what C is. So we've used that pretty consistently. C is your centering point. X is the number that we plugged into the series. So you'll have to get into the specific question to see what that is. So I'll just put this was the plug-in. It's where you evaluated the series at. N is simply your degree, right? So if you use think of it like this, if you use the 4th degree Taylor polynomial, N is 1, so what's N, or N is 4, excuse me, so what's N plus 1? 5, right? So again, N is simply has to do with degree. And then our favorite letter here. This is the one that always messes with people. The letter Z. Z is simply some number on the interval from x to c. Some number in closed interval, some number in between there. What is the Z value? We don't know. It kind of depends on what we're given and what we know about all the stuff that we've got in front of us. Sometimes we're going to know a lot. And I'm going to start you off with one that we'll know quite a bit. It's not going to be that hard to figure out. Later on, it'll be a little shakier. And at the end, if we get to it today, which we probably won't, probably be on Monday, you're going to be like, whoa, I don't really know anything about this. But wait, maybe there's enough info over here or over here. Okay? So we'll kind of go from like fairly concrete to, I'm not sure, to I need some help. That make sense? Kind of go in that order. Okay. So like I said, this is where you might have to do a little bit of thinking to various degrees. Sometimes it'll just be a very little bit of thinking. Other times it'll be a lot of thinking. The other two are extremely formulaic. Just plug it in, chug. Plug and chug, done. All right. So let's see here. Let's look at example number 1 together. And I'll just kind of take you through. We'll go back and forth. You can ask questions. We'll just kind of work this one together a little bit. First 4 terms of the Maclaurin polynomial for e to the x. You can see that agrees with what you just did, right? So this says, use Taylor's theorem to approximate e to the point 1 by using your polynomial evaluated at point 1. This would, if we were going to do this in this form, this would certainly be a calculator active question if we wanted you to get to a kind of a final simplified decimal. So let's use your calculator, okay? Take a minute, practice this out. Let's figure out p of 0.1. A value for that? 1.105? Okay. 1.105. Got like 3 or 4 folks that are convinced of that. Rest of you guys okay with that number?
So to approximate that, did you just do e to the point 1 in your calculator? Or did you use the general series?
So we're we're definitely looking at 2 different things here, right? So the wording is precise, but it's easy to confuse. So it says, use Taylor's theorem to approximate. So we are not finding the exact value of e to the point 1 because we're approximating it, and we're going to use the polynomial that we have to approximate it. So we're definitely not doing e to the point 1.
You just plug in point 1 to the feedback.
So this one is kind of tricky because we're going to explore a little bit with it because people are going to say, and I get why you would say this, you'd say, why would I need to discuss anything about the error? Couldn't I just use my calculator and figure out what e to the point 1 actually is, do a little subtraction, and it's over with? I get it. I totally get it. I'm trying to build this up with something really simple. We're going to get to a place where you look at it and you say, whoa, I don't get the calculator for such and such. How am I? That's what we're building towards. So suspend a little bit of disbelief here as far as what you could or couldn't do with a calculator. You guys all okay with that value? Okay, so let me help you think this through. It goes on to say, and show that the maximum error for this approximation is less than, and that's a pretty tiny number, 5 times 10 to the negative 6th. We're supposed to show that our error here is less than that. Apparently that's the standard by which we've decided it's okay to be off by that much. As long as we're off by less than that, we're good. So, if this were an alternating series, which it is not, but if it were an alternating series, wouldn't we need just one thing to help bound the error? What would we need? First neglected term. If it was a converging alternating series, you just find the first term you left off, and there's your maximum error. But it's not an alternating series. There's not even any minuses anywhere. It's just plus, plus, plus. And even if it was plus, plus, minus, plus, plus, minus, 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 plus, that's still not an alternating series. So we've got to use this Lagrange error bound. Here's how we would do this. I'm going to say something like e to the point 1 minus p of point 1 That's my error, right? Actual value minus what I just found for my approximation. That's my error. Is less than or equal to. So the first part is really formulaic. It's x minus c to the n plus 1. So what's my c value? Centering point, which was? 0. And what's the number that I plugged in? The x value? 0.1. Okay, so absolute value of 0.1 minus 0, all to the n plus 1th power. So what was n? What was the degree that we used to get our approximation? Third degree. So n plus 1 is 4. So this to the 4th power, all divided by n plus 1 factorial. So 4 factorial. And that concludes the formulaic part, where you just plug in an x and a c and an n, and hopefully it just takes you 5 seconds and you're done, right? Very formulaic. You don't have to think terribly hard about that. Max value of the n plus 1th derivative, right? So in other words, what's the max value of the 4th derivative? What's so easy? What's the easy part about this? What's the 4th derivative? What's the any degreeeth derivative? It's e to the x. So that makes this a little bit easier. So you say, all right, maybe you make a little note to yourself off to the side, and you're like, all right, the 4th derivative is going to be e to the x. And we start to think, well, what would be the maximum value of that on the interval from c to x, from 0 to 0.1? Maybe a graph would be helpful.
I mean, it would just be 0.1.
Let's think about what the graph would look like. I think we'll get to that conclusion. So here's the graph of e to the x. Looks something like this. So here's 0. 0.1 would be over here somewhere. So if we understand the graph of this, and if you had the calculator, maybe you would, if you didn't know e to the x, you'd graph it real quick. So let me ask you, if we're looking for the max value of the 4th derivative, evaluated at z, where z is some number on our interval from c to x, what would be my z value here? Where does the 4th derivative have the biggest value? 0.1. Because isn't e to the x strictly increasing on this interval? Yeah, so the right endpoint. So I'd come over here and say, you know what? The max value of my 4th derivative would be e to the 0.1. Max value of my 4th derivative. My 4th derivative is e to the x. The maximum value of it will happen at that far right edge. Be pretty unreasonable to expect you to do this without a calculator. So take a minute. Some of these will be reasonable for you to do, but not this one. E to the 0.1, I don't know what that is. So if you guys would take a minute and calculate that out.
So if it were just some other function that's not doing that.
Yeah, that's where you have to do a little more
interval?
thinking.
Is it from 0 to whatever you want?
It's not 0 to whatever you
0 to
want.
0.1?
Yeah, it's like you start off at your centering point and you go to whatever your plug-in was.
And whatever that is.
What's hard about these is when the max value of the 4th derivative takes place somewhere in between,
Yeah,
like
then you
not on an endpoint. Because like you said, like it does one of these things.
Yeah.
How do you bound that exactly? That's where you have to do a little more thinking. This one you didn't have to do a whole lot of thinking. Okay. Some of the later ones you'll be like, what?
Yeah, that could be a hefty problem.
Yeah, yeah. And in some situations you'll know less and less about like the n plus 1th derivative. And so I either have to give you more information or some other clue about how you're supposed to deal with it. Or the calculator needs to be active or something. Yeah. Well, what number did you guys get for this? Did you get one? No?
4.2.
Okay, so say it one more time. 4.605 times 10 to the negative 6th. Okay. You guys get the same thing as Jasmine did for this? Yes, you did. There we go. Okay, so you can see this is a really tight window, but this actually is less than 5 times 10 to the negative 6th. Does that make sense? Liz?
So what happened to the z?
What happened to the z?
Yeah.
Nothing. It's right here.
How come not z?
How's,
Like,
so z is some number between x and c inclusive, right? In closed interval, right? And so this notation right here means the n plus 1. So in our case, the fourth derivative, right? Fourth derivative evaluated at c. Or evaluated at z.
and z is wherever the maximum of that.
Z is the x-coordinate for wherever you think the biggest value of that n plus 1th derivative happens.
Okay.
Yeah. Sometimes we don't even write the z.
The furthest end that
Sometimes we don't. Sometimes we'll say, yeah, z's like right about here, and then we'll just look what the max is. And we'll just replace that fourth derivative at z with whatever the output.
Value.
And that's e to the 0.1.
Yeah, yeah.
That's what we're estimating the max value to be.
n plus 1.
Josiah?
So if we were to just do that, it'd be the next term.
Like say
Then we
the
multiply it by this
fourth
whole
derivative
max
of
in that area.
f of x,
Yep.
was decreasing on that interval,
Yep.
would you use 0?
Yep.
as the max?
Yep. You'd say your z value would be 0 then, and so it'd be whatever evaluated at 0.
Okay.
Yep.
Um,
And like Nick was saying earlier, like if you've got a strictly increasing function, it's the right endpoint. If you got strictly decreasing, it's the left endpoint. But what if it does one of these?
so like, is
Can
there
be harder.
any situations in this where you'd be able to use a no calculator, or most
Yeah.
of the time there will be?
Yeah, you'll see some in our packet
Okay.
for sure.
And then the second question is,
Yep.
What did you do to say that just f to the fourth, f, like fourth derivative of x equals e to the x?
So I just recognized since the function that created my Taylor series was e to the x,
Yeah.
the first, second, third, fourth, fifth, sixth, seventh derivative of e to the x is just e to the x,
Okay.
right?
Okay.
Since the derivative of e to the x is e to the x, no matter how many derivatives you do, the result will just be e to the x.
I'm just a little confused, like if that power, if the p of x isn't like being like added infinitely,
Mhm.
how is that equal to e? Like, could you say that 1 plus x squared over 2 factorial is equal to e to the x as well?
Whoa, say that one more time? Oh, you're asking how is p to the x equal?
No.
Are you talking about that?
Yeah.
So p to the x is just a polynomial.
Yeah.
P of x, excuse me. So p of x, that's just that polynomial.
Yeah.
And I could not say this. No way. I cannot say that. I can, however, pretty comfortably say that. Right? E to the x is approximately equal to p of x, and p of x equals that polynomial.
Okay. I guess the way that I was looking at it was using the p of x, since I recognized that as the power series for e to the x.
It's not the power series yet. It's just a polynomial. Now, if we put on the end, if we put plus ... x to the n over n factorial, and we said, hey, the n will just go on forever and ever and ever, now we can say it's equal to e to the x. But as it stands, I've just written 4 terms down,
Yeah.
and in no shape or form does e to the x equal that.
Okay.
But e to the x is approximately equal to
Anytime
that.
with
Yeah.
no
So the way
notice.
I was thinking it was like the one, like this is wrong, but like saying that one is, you know, f of x. X is
F of 0.
Yeah, x is the f
Yep.
0, all that.
Now,
So I was
at the centering point, which is 0, that polynomial will equal e at its centering point.
Let me know.
So in other words, e to the 0 equals that with 0 plugged in, right? Remember, so when you're at the centering point, the function and the polynomial will be exactly the same. But if you're going to say e to the x, we're not at the centering point, we're at anything. That's where you can't say that.
Tree gets done, and then we'll just.
That make sense?
Alright, so I'm just, I'm still, I can have some extra class
You might be kidding. You know what? I never defined the function for this. I never called e to the x anything. What So I probably should write f of x
Oh, that's,
equals e to the x.
Yes,
You're thinking f and p are the same thing.
Yeah, I keep thinking like,
F and p aren't the same thing. F is referring to some generic function.
yeah, so I might think like,
No, P is different than yeah. I should probably edit that. Yes, sir.
So this is kind of like a basic question, but I just want to make sure I have like a complete understanding. Why is this a third degree Taylor polynomial?
So degree refers to exponents,
Oh, okay. Wait, that makes
and it
sense.
could be like like with cosine, 6th degree only has 4 terms.
Oh,
right?
okay. Yeah, because it goes like.
Yeah, so we'll refer to them like both ways.
Okay.
You might be asked to write the 5th degree polynomial for whatever, or write the first 4 non-zero terms, and it could be kind of the same thing or it could be different.
Okay. Every time I heard degree, I thought of it as the same as like the number of terms.
Yeah, just exponent.
Okay.
Yep.
Thank you.
Yep. Yes, sir.
So, since we know concretely that what e to the point one is and what minus p to the polynomial to the point one is, why do we have to say less than or equal to?
So this is what I said earlier. You need to kind of suspend your knowledge of the fact that you have a calculator in front of you.
Yeah, I do. No,
Right? So I'm trying to start you off with something that's like really graspable and the easiest version. Just wait. You're going to get to a place where we're going to do these with no calculator and not many other tools. So I was trying to start you off with something like, hey, if you really wanted to just find what e to the point 1 is, it would take you 5 seconds, right?
Yeah.
I get it. So do we really have to do that for this one? No, we don't. But later on, we're going to need the tools that we're using right now.
So mathematically, could you actually calculate this and figure out definitively, in this case, is it less than or is it equal to?
We could figure out the exact error, or we could at least approximate it to like the 20th decimal place just using our calculators. And I don't care about that because we don't really need to do that here. We need to be able to do it without a calculator. But I thought, like I said, I'd start you off with one that's like, you can grasp it fairly easily. So you're almost like confusing yourself because like, why don't I just use a calculator? Well, on this one, why wouldn't you?
Yeah.
Later on, it's going to be different. Okay. Okay, so guys, I hope, listen up please, listen up. I hope that me answering the in-depth questions that I have today has been helpful. Listen up please. I wanted to try to answer those. I did want to try to get into example 2 today, but I decided to do some more in-depth question answering. I think we'll be fine. I think we'll be fine on Monday. Monday there is an intro video for Power Series, and we'll just kind of. I think we should be fine, just kind of transitioning right into that for Monday. I think that'll work pretty well. So I think I'm pretty happy with this because you guys are going to get one more chance to construct a Taylor on Monday. We'll do a couple more Lagrange error bounds. They'll get progressively a little tougher. I think we'll be okay. So anyway, good job. Have a great weekend. See you Monday.